For PAL 5 modeling sinusoidal situations, the situation I chose was musical notes. The question I had chose was, do sine waves for combinations of musical notes that sound good to us look different than sine waves for combinations of notes that sound bad to us? First thing that needs to be defined is notes. Notes are defined by their frequencies, which was established before the notes had names. For example, our Western note system started with the frequency 440, which is A4, and got expanded on different pitches like 550, 660, and other frequencies that sounded good together. Eventually, there were 12 notes until the cycle repeated at A5, which is an octave higher at 880. With those 12 notes, people listened for frequencies that sounded good with them. One completed cycle of notes is called a scale. Gradually, all the scales got completed from the fourth iteration to the fifth iteration. Another definition is frequency, which is defined by how many cycles per second the sound is. So, for example, A4 has a frequency of 440, which means 440 cycles per second. The good sounding notes used to see the relationship between good and bad sounding notes is an A chord. The notes in the A chord are A, which is 440, C sharp, which is 550, and E, which is 660. The formula for graphing the notes is f of x equals sine 2 pi times the frequency x. The original formula for a sine function is a sine b x minus c plus d. A is the amplitude, which is the loudness of the note, which for simplicity can just be left as 1. C is the phase shift, which doesn't apply here either because it doesn't affect the note's frequency. D also doesn't affect the note's frequency, so that can be left out as well. Now the formula is sine b times x. For the rest of this formula, let the frequency be represented as f. B is equal to 1 cycle, so the B value is 1 over f. Since f is how many cycles are in the second. Since 1 over f is the period, when putting the formula into the equation, it comes out to 2 pi over 1 over f. It can be rewritten like this. To divide fractions, the sign is switched to multiplication, and the numerator and denominator of the last fraction are flipped, making it 2 pi over 1 times f over 1, which just equals 2 pi times f. When 2 pi times f is substituted for b, the formula is sine 2 pi times fx, and with that, the graphs can finally be graphed. The following graphs will be accompanied with the note they're visualizing. A known chord that sounds good is the A chord, which consists of A, C sharp, and E. This is what the A and C sharp notes sound like when played together. And here's what that looks like. The two graphs cross the x-axis at the same point 2 times, here and here. It's pretty similar with the A and E notes. Now these two notes cross the x-axis in 4 different spots. Lastly, A4 and A5, which are called octaves, also sound good together. Here, the notes cross the x-axis at the same point 8 times, which seems obvious because A5 is twice as fast or frequent as A4. When comparing graphs of notes that sound bad together, they look a lot different. Here's A and D. Doesn't sound too bad, but when comparing the graphs, there's no point on the x-axis where they meet. A and D come really close to meeting at some parts, but they don't actually meet. If you keep going right as well, there's still no point on the x-axis where they meet. It's the same with the rest, like A and B flat, A and E flat, and A and B natural. A and B natural specifically, which sound particularly bad together, are really far away from each other when compared to the other notes. From this data, it can be concluded that notes that meet on the x-axis sound good together, which are called consonant notes, and notes that do not meet on the x-axis sound bad together, which are called dissonant notes. To make this problem more complicated, I would be doing it with chords. It was mentioned earlier that the A chord is A, C sharp, and E, but since there are so many iterations of chords, it would be a lot harder to analyze so many graphs.